Hey guys, today we're going to take a look at an implicit differentiation question that uses chain rule. So on the right side of our equation, we notice that the sign is getting squared. So I'm going to rewrite that squared on the outside of the entire trig function with brackets, just so that I can keep track of my layers. The middle layer is the sine function itself, which I'm going to color code in blue, and the innermost is the angle, which I'm color coding in yellow. So with chain rule, you always work from the outside in. So I know that I'm going to start with doing the derivative of the red, then the blue, then the yellow. So on the left-hand side, the derivatives aren't too bad. We're just going to apply power rule with our implicit for both of these terms. The right-hand side is where it's a little bit more challenging. The outermost layer, we have something getting squared. So I'm going to bring down the 2 to start that derivative, and leave everything on the inside the same, so I'm just going to use the brackets as a placeholder, and drop the 2 to a 1. So the inside does stay the same. We only did the derivative of something getting squared, so I'm going to leave sine of 9y exactly the same. Next up, we need to do the derivative of the blue part, which is the sine function. We know that if you have sine of an angle, the derivative of sine becomes cosine of the angle. So we have cosine of 9y. Again, that innermost part will stay the same here, so it's still a 9y. And then finally, we do the derivative of the yellow part, the innermost part, and the derivative of 9y in this case is 9 dy dx. So now we have our derivative. And from here, it doesn't look great, but we need to try to find a way to organize this, because ultimately we need to isolate dy dx. So a couple things. The right-hand side is just one giant term, and that giant term has two numbers that we can multiply together, the 2 and the 9. So I'm going to take note of that before I start moving things around. The other thing is that there are just 3 total terms here, and one of them doesn't have a dy dx in it. That's our 15x squared. So I'm going to move all the dy dx terms to one side and all the non-dy dx terms to the other side. So that 15x squared is going to end up on the right-hand side, so we're going to leave our 16y dy dx on the left. And now I'm just going to bring that entire thing on the right-hand side to the left-hand side. There's that 18 out front from the 2 times the 9. And I'm just rewriting that entire expression. The right-hand side is just your 15x squared. And now we're in pretty good shape. We have 2 terms on the left-hand side. We can see that both of these terms have a dy dx in them. So my goal here is to pull out the dy dx as a GCF. We'll write in the 2 terms that are left behind. Remember, if you start with a certain number of terms, then you pull out a GCF, you'll always be left with the same number of terms. So we started with 2 terms, we pull out a GCF. I still have 2 terms on the inside of the parentheses, I should say. The inside of the parentheses, the number of terms will always match what you started with. And now we're essentially done. Now I just need to divide both sides by that mess on the inside of the parentheses, and dy dx will be isolated. I would recommend with problems like this that you guys take a look at the graph on Desmos. Keep in mind that usually with derivative functions, they give us all the possible slopes. But on these crazy functions, you need both an x and a y to plug in order to find the slope. So I'd recommend taking a look at some of the graphs and just getting a sense of why you need both an x and a y in order to figure out the slope at a point.